All right, welcome to this week's PLS. Our speaker, Dr. Russell Callahan from the University of Russell is an assistant professor in the Earth Science. Been on the East Coast for the last couple of years. He's actually spent lots of time in the West, about arid and semi-arid. Undergrad at Montana State, doc at the University of Wyoming, and other postdocs. So Russell's a geophysicist that uses geophysical methods, which I'm sure you all will hear lots about, called Deep Critical Zone Controls on Hydrologic Processes. We're going to chat.
Great. Thanks, Sarah. Thank you all for being here today. I've enjoyed my visit so far. I think I might have brought the snow with me from Connecticut, so hopefully you all are enjoying the winter weather. So today I'm going to be talking about this landscape in the Central California Coast Range, just east of San Jose. And I'm going to be talking about how, in order to understand the hydrological processes operating in this landscape, we actually need to go beneath the hill slope to think about the subsurface structure. Before I get started, I just want to acknowledge my collaborators on this work. So this was work I did during my postdoc at UC Santa Cruz with my postdoc advisor, Margaret Zimmer. I also had the pleasure of working with Menghan Wang, who I think a lot of you all know. I guess he was here a couple semesters ago. Then also Daniela Rimpe at UT Austin. And then some of the work I'll be sharing today was led by graduate students Amanda Donaldson and Narissa Barling. Also the work was funded by the National Science Foundation as well. So wanted just to acknowledge all of these folks. And so I wanted to start by motivating this talk. This plot is probably not too surprising to many of you. This is a projection of Earth's surface temperatures under different emission scenarios from the 2022 Intergovernmental Panel on Climate Change Technical Summary. And regardless of which emission scenario we use, we see that Earth's surface temperature is expected to increase, is increasing, and is expected to increase even more in the future. And this is leading to large changes in hydrology and in vegetation across mountain landscapes. Now, for example, here we have examples of tree mortality across 4 different places across the globe due to increasing temperatures as well as widespread droughts. And in this image here, I'm going to show you forest loss since 2010, defined as areas that have greater than 20% change in tree canopy cover, shown here in red. And you can see that this forest loss is pervasive across not just the western U.S., where we often think about forests, but also in other parts of North America as well, in the southeast, across Canada. So while not all of this is due to a changing climate, there's also urbanization, land use change in here as well. This is a widespread phenomenon across the world. Likewise, the changing temperature and climate change are expected to change surface water resources. So this is a modeling study which modeled changes in stream flow across the globe under changing climate. And as you can see, the variations are different depending on the geographical area, but generally we're expecting a decline in stream flow under climate change across much of the land surface area. And so hopefully, this is some good motivation to study hydrological resources in mountain landscapes. And what specifically I want to talk to you about today is that in a lot of landscapes, I think we need to go beyond thinking about just the surface and the shallow soil, but also think about the deep weathering structure that exists within hill slopes. So going beyond the soil into this weathered bedrock zone to really characterize the subsurface and understand these hydrological processes. We know that the subsurface is an important modulator of the water cycle, but there's still a lot to be learned about how the subsurface structure, especially in the deep critical zone, modulates how water is stored and rooted within watersheds. And, as I've kind of already touched on, I think this is particularly important in the context of climate and environmental change. So some of you all may be asking yourself, what is he talking about with the critical zone? So let me just define that here quickly so we're all on the same page. So the critical zone framework has kind of been in existence over the last 20 to 30 years, which is this framework for understanding Earth's surface environment from fresh rock at depth to the tops of trees on Earth's surface. And this has brought together researchers, across disciplines in geology, ecology, hydrology to kind of better understand the interactions that happen within this zone more holistically. And today, especially in the first part of my talk, I'm going to be talking about the subsurface layer in the critical zone. So this is an image from the Front Range in Colorado, and it nicely illustrates the different layers we might expect to encounter in the critical zone, where we have fresh rock at depth, which has that nice gray granitic color down here. And then moving closer to the surface, we have fractured bedrock, where we can start to see some abundant fractures and signs of iron oxidation with that red color, and indicating that physical and chemical weathering processes are breaking down the bedrock. And I'll also be talking about saprolite. So saprolite is a term to describe the zone on the surface just below soil, between fractured bedrock and soil, where the rock retains the fabric of the underlying rock, but is intensely chemically weathered and has lots of porosity. And I'll touch on how this is a really important source of water storage for vegetation in some of these semi-arid landscapes. Okay, so now that I've defined what this different terminology I'll be using, let me take you to our study area we'll be talking today. So this is Arbor Creek Experimental Catchment, outlined here in red. This is just east of San Jose in the California Coast Range, kind of right just east of the South Bay over here. And in this landscape, we're focused in on this really pretty small headwaters catchment where we've, or the catchment's been instrumented with different hydrological measurements, as well as some geophysical and drilling measurements, which I'll be talking about more today. So in this landscape, we are interested in kind of two big, jumped ahead. First, let me introduce the climate and characteristics of this catchment. So as much of California is in a Mediterranean climate, meaning there's a winter rainy season that's, we're kind of in the middle of right now. And then in March or April, things will start to, the climate or the weather will start to change, and we'll enter a prolonged dry season where it'll be dry for 5 or 6 months until, October or November. This catchment receives roughly 500 millimeters of annual precipitation, pretty much all falling as rain. No snow in this part of the world, or at least very little. It's a thin soil with just about 50 centimeters deep, and a sandstone and shale lithology, which I'll be talking about in more detail later on. And as you can see here, there's also aspect-controlled vegetation, with grasses characterizing the south-facing slope and oak woodland vegetation characterizing the north-facing slope. So we're interested in kind of two big picture research questions here. First, how does the deep critical zone control water partitioning throughout the catchment? And water partitioning meaning, after rain falls, does it contribute to stream flow? Does it recharge groundwater systems, or does it, is it stored and then used by vegetation? And then the second question is, how do these aspect-related differences in vegetation dictate subsurface moisture dynamics? So first, I'm going to touch on how we can characterize the subsurface critical zone using drilling and geophysics. And then I'm going to talk about connections between weathering, tectonics, and groundwater hydrology. And then in part two, I'll shift gears and talk about aspect-related differences in vadose moisture dynamics across the north and south-facing slopes here. Okay, So as part of this study, we were able to drill into the critical zone to directly characterize the subsurface material. So we had this track-mounted drilling rig, which was able to recover intact cores of the weathered sandstone and shale within this catchment. We did this at N4W1 on this this ridge top above the north-facing slope, and S3W1 on the ridge top above the south-facing slope. And so I'm going to quickly walk you through just what we found the different weathering layers to be in the subsurface. So, this is a cross-section of topography and the different, the borehole locations with the different weathering layers shown here. So in the top, we have soil and saprolite in the top, 3 meters on north-facing slope and 5 meters on the south-facing slope. We have this soil and saprolite, which is highly disaggregated and has matrix oxidation throughout. Below that, we have fractured bedrock with both matrix and fracture oxidation. You can see, those reddish colors throughout, indicative of that oxidation and weathering in this zone. And then below that, we have the zone where, this is about, 17 to 20 meters below the surface. We have fractured bedrock where, most of the oxidation is kind of restricted along those fracture planes. And there's less oxidation within the bedrock matrix itself. And then finally, at the deepest part, 24 meters below the surface on the south-facing slope and 36 meters on the north-facing slope, we have fresh bedrock where there's no signs of chemical weathering, but there is, still significant fracturing in the subsurface, especially in this zone on the north-facing slope. So we'll get back to, what's driving this deep fracturing here in a second. So these are nice because we can, directly see what the subsurface material looks like, but we can also take this a step further to look at, how the chemical weathering is varying across these landscapes. And so we subsampled these cores, sent them for bulk geochemical analyses, and we can look at chemical weathering trends with depth. So what I'm going to be showing you here is a plot of tau, which uses an immobile element titanium and a mobile element to show how mobile elements behave throughout the weathering process relative to their concentrations in the unweathered bedrock. So if you plot positive in this tau plotting space, that's indicative of a gain of that element during the weathering process. And if you plot in the negative space, you'd expect this is indicative of a loss. That's where we would generally expect the plot for weathering reactions. And the more negative you are, the more of that element that has weathered. So let's take a look at two mobile elements here, magnesium and sodium. On the south-facing slope, we can plot these trends with depth. And you can see that as we move towards the surface environment, some of these elements like magnesium, sodium are becoming depleted. And here's the north-facing slope, also plotted here. And we can see that in some places, these elements are depleted, 20 to maybe even 30 meters below the surface, suggesting that, the observations of the deep weathering from the cores are also indicative, are also indicative of chemical mass loss from chemical weathering processes. And I just also wanted to mention this is much deeper than we might expect to see in a semi-arid landscape like this. So as I mentioned, these observations are consistent with the visual observations from the core. And also we took, rock chips and measured matrix porosity. And we can see that the porosity generally increases towards the surface, indicating that these weathering reactions, which are depleting these mobile elements, are also creating porosity in the near the surface, which is important for subsurface water storage and movement. Okay, so this kind of summarizes the borehole measurements of weathering here. But we also wanted to understand, whether these trends are consistent across the landscape or whether these are, just from the two are whether it's broadly representative, the boreholes are broadly representative of what's going on elsewhere in the landscape. So we used seismic refraction surveys to quantify the spatial variability in weathering. So for those of you who are unfamiliar, seismic refraction works by placing a geophone on the ground surface, which records vertical ground motion, and you lay them out in a string or in a straight horizontal line. You then create seismic energy using a sledgehammer and metal plate, and those waves, primary waves, travel through the subsurface and then arrive at each of those geophones. Then we can pick those first arrivals and use a geophysical inversion technique to create a velocity model of the subsurface. And the velocities in the subsurface are dictated by the elastic properties of the rock in which the waves are traveling through. And in the near surface, that's mostly dictated by the fracturing and chemical weathering that's happening. So, these are some rough guidelines of the different P-wave velocities for different subsurface materials. So for soil, we would expect velocities on the order of, less than 500 meters per second. Saprolite between 500 to 1500 meters per second. And then that weathered bedrock for between 1250 and 3000 meters per second. And then unweathered bedrock, having velocities of around 3000 meters per second for this, sandstone lithology. And so when we actually look at the seismic refraction results from this landscape, we can see a few different things. First of all, we have this 1200 meter per second velocity contour shown here in red. Based on the borehole information, this corresponds to the transition between saprolite and fractured bedrock in this landscape. And then also more generally, we have really slow velocities pretty deep within the subsurface, indicating that this deep weathering exists across the landscape. So, our geophysical results are kind of corroborating what we observe from the boreholes. Okay, so this raises the question, what causes this deep fracturing and weathering? So there's a few different possibilities. Based on the geologic context of this region. So first of all, we are located in the California Coast Range, which is part of the Franciscan Melange, which consists of sedimentary rock that has been subducted beneath North America and then uplifted as part of the California Coast Range. And during this, there could be substantial deformation and reorganization of the rocks during this uplift process. In fact, we see some high-grade metamorphic minerals just adjacent to the Arbor Creek catchment, where we have the mostly metasedimentary bedrock, suggesting that there's been substantial reorganization and potentially fracturing associated with the uplift. We're also pretty close to major faults. This is the Calaveras Fault, which is a branch of the San Andreas Fault system right here. And from INSAR imagery, we can look at slip rates to show that this fault is active. Here's Arbor Creek shown over here. And some of the strain that builds up along the fault, as well as shaking during earthquake events, could potentially cause fracturing in the subsurface and help contribute to the fracturing we observed here. And a final possibility is that there's been some work showing that subsurface stress fields from the regional tectonics and topography can also cause large amounts of fracturing, especially beneath ridge tops, which could be contributing to some of these patterns. So there's more work needed to kind of tease apart these different potential drivers of fracturing, but here's just a couple of examples of what might be driving the patterns we see here. Okay, so now let's dive into the hydrology bit a little bit more. So at these borehole locations, we instrumented, we had groundwater level recorders, which were deployed, kind of through the rainy winter season at both S3W1 and N4W1. And what we see is that the groundwater level aligns with the depth of oxidation at both N4W1 and S3W1 consistent with a hydrologic control on chemical weathering. And this is something that's been described in other landscapes where, the general idea is that in order for the weathering to take place, you need to exhume the bedrock above the above the water table so that, fresh meteoric water rich in oxygen can then come in and cause those weathering reactions to take place. Whenever you're below the water table, the water's usually saturated in solutes and unable to, cause those weathering reactions to take place. And then we also have this in-stream well down here. And this groundwater level in the in-stream well is just below the surface, except for these intermittent stream flow generation events, which happen during the really intense rainstorms that we get in the winter in this landscape. Okay, so putting this all together, this is our conceptual model of weathering and groundwater hydrology in this landscape. So the subsurface is highly fractured and the weathering fronts reach 30 to 40 meters below the surface. And this fracturing, we think, causes high permeability, which leads to a deep water table that is largely insensitive to topography. Typically we would expect this groundwater table to mirror topography, but instead in this landscape, due to the high permeability, it just seems to be just flat. And we think this may help contribute to interbasin water transfer in this landscape because doesn't seem like very much of the incoming precipitation is exiting the system via stream flow. And additionally, the chemical weathering reactions seem to be controlled by this water table where, the onset of the chemical weathering happens once the rock is exhumed above this water table here. Okay, so this is that's the end of the first part of the talk, and now I'm going to shift gears a little bit and talk about aspect-related differences in veda zone moisture dynamics. Water real quick. Okay, so aspect, or the direction a hill slope faces, leads to large differences in incoming solar radiation or insolation between adjacent hill slopes. And so, you can see this in lots of different landscapes, including, I'm sure if we looked outside, we could probably find an example pretty quickly. In the northern hemisphere, the south-facing slope has more insolation and is generally warmer. And the north-facing slope has less insolation and is generally cooler. And as I said, these patterns are widespread across much of our land surface area, with south-facing slopes having greater insolation in the northern hemisphere and north-facing slopes having greater insolation in the southern hemisphere. And these variations in insolation can then also lead to differences in evaporative demand. So we might expect that the south-facing slopes have a higher evaporative demand and therefore are drier, and the north-facing slopes have a lower evaporative demand and therefore are wetter. However, these conceptual models don't really consider vegetation water use patterns, especially from this weathered bedrock zone, which I talked about earlier. So to evaluate, this kind of conceptual model and include the role of vegetation, we took an approach using remote sensing as well as measuring moisture dynamics in the field directly. So we first wanted to understand how the evapotranspiration, that is the total flux of water from both evaporation directly from the surface and transpiration, the water used from trees and grasses in this landscape, vary across these two different hill slopes. So we use this OpenET remote sensing platform, which has estimates of OpenET from different models and remote sensing products and aggregates them into a single ensemble measurement. And so we looked at ET across the north-facing slope here and the south-facing slope here. And what we see, which is probably not too surprising to you all, is that the higher evapotranspiration on the north-facing slopes with that oak vegetation. So, you can see that for all 5 of these water years that I'm showing you here, the north-facing slope has greater amounts of evapotranspiration than the south-facing slope with the grasses. And so we wanted to take this a step further to actually understand what could be happening in the subsurface. So we used this method called the root zone storage deficit, which allows us to, use the evapotranspiration data in addition to precipitation data to calculate a deficit of water in the subsurface based on these 2 measurements. So I'll walk you through here how this works. So we're going to take precipitation through time and evapotranspiration through time, and we're going to calculate this deficit over here. A greater deficit means the subsurface should be drier, and a lower deficit indicates a wetter subsurface. So in this first time step here, where we have precipitation exceeding evapotranspiration, a deficit does not, we don't have a deficit because the water that's leaving the system via evapotranspiration is sourced, from this incoming, can be sourced as an input from this precipitation here. Again, in this intermediate time step, precipitation equals ET, so we don't incur a deficit. But here at B, our evapotranspiration now exceeds the precipitation over here. And this indicates that this evapotranspiration must be sourced from water stored in the subsurface. So we have a deficit of 2 units here that develops. Moving forward in time, that deficit then, becomes greater as evapotranspiration, stays at the same level and we receive no incoming precipitation. And then eventually, if precipitation exceeds evapotranspiration, then that deficit goes back down. So this is just a simple way of, summing precipitation inputs and evapotranspiration outputs to calculate a deficit in the subsurface. And then eventually in this last step, we'd eventually have enough precipitation to go back to 0 in this deficit calculation. So we added the precipitation data here and used that evapotranspiration data that I just showed you to estimate root zone storage deficits across both hill slopes. And here I'm showing you the south-facing slope where, we seem to develop a deficit each year once that transpiration kind of kicks in and the precipitation stops. But then once that precipitation starts at the beginning of the next water year, that deficit then returns to 0. So in the south-facing slope, the root zone storage deficit is always replenished. But on the north-facing slope, we see a different pattern. The root zone storage deficit is not replenished, at least over this period of time, because the evapotranspiration is great enough that in some cases the incoming precipitation the next year does not refill that subsurface storage. And this leads to this kind of actually unrealistic runaway root zone storage deficit here. Eventually this would have to be replenished, or else there would be negative water in the subsurface. But this is just to illustrate that there are some uncertainties with these evapotranspiration and precipitation estimates. But this is just to illustrate that the north-facing slope, we would expect larger root zone storage deficits, and in some years they may not be replenished, and you need to source water from the previous year's precipitation. Okay, so let's go to this conceptual model here. And on the south-facing slope, we have, we showed with the remote sensing data, we have less evapotranspiration, and this would lead to a smaller root zone storage deficit. On the north-facing slope, more evapotranspiration because of that oak vegetation and a larger root zone storage deficit. But what's actually happening within the subsurface? So rather than just rely on remote sensing here, we wanted to directly measured the subsurface moisture content. So we used these boreholes that I was talking about earlier to directly monitor the Vadose zone moisture dynamics. So we used 2 boreholes on the north-facing slope and 2 on the south-facing slope. And we used neutron probe measurements. And so neutron probe measurements use a radioactive source, and they emit neutrons from this probe down here. And the neutrons, basically are sensitive to the hydrogen ions in the subsurface and will bounce back to a receiver here, or a counter here that is telling you, how much of the radioactive source is returning back. And so these are really sensitive to variations in water content. And so a higher neutron count is indicative of a higher subsurface water content. And so we did this at throughout the growing season, starting in March, the wet start of the growing season, through October, the dry end of the growing season. And we did this, again, on the north and south facing slopes. And here I'm going to be showing you from March to October of 2023. So 0 equals no change, meaning the moisture dynamics were the same at the beginning of the growing season and the end of the growing season. And a higher difference means more depletion or drainage, meaning the subsurface was much drier at the end of the growing season than at the beginning of the growing season. And so what we see here is that on the north-facing slope, we have this, large amounts of change in the, down to 10 meters in some cases. And we also have this interesting blip here, which we think may be due to a fracture zone here. And then on the north-facing slope, the south-facing slope, we still have, some depletion, but we have larger and deeper depletion of bedrock water storage on the north-facing slope, kind of consistent with that idea from the root zone storage deficit calculations. So to corroborate this and go beyond the individual boreholes, we also did some time-lapse electrical resistivity measurements. So electrical resistivity measurements are done by putting metal stakes in the ground and injecting a current and then measuring the voltage differences in the subsurface. These differences in the subsurface can be due to differences in clay content or differences in mineralogy, and also differences in moisture dynamics. So assuming that, these 2 hill slopes have similar subsurface structure and similar amounts of clay, which based on our understanding of the site is a pretty good assumption, we can say, we can infer that the higher resistivity values are indicative of a drier subsurface and the lower resistivity values are indicative of a wetter subsurface. So this is from our first resistivity survey in June. And we can see that if we take the averages across the hill slopes, generally the north-facing slope has higher resistivity values indicative of a drier subsurface. And here's the results from a July survey. And you can see, more of these red, higher resistivity colors on the north-facing slopes, indicative, of those drier conditions compared to the south-facing slope. Then finally, in our last survey, we get even more of that red on the north-facing slope, suggesting that, again, the north-facing slope is drier. And then finally, we can look at the change in resistivity. So here, the red colors represent an increase in resistivity from June to September. And then the blue areas represent a negative, would be decrease in resistivity here. So, these difference plots do look a little bit noisy, but I do want to just point out these, really high, these really dark red colors indicative of a increase in resistivity, which would be a drying of the subsurface throughout the growing season. And when we look at where the vegetation is along this hill slope transect, we can see that a lot of those red colors generally correspond to areas where we have this woody vegetation. Even up here on the, kind of the other side of the ridge above the south-facing hill slope. And, this is consistent with the, these differences in evapotranspiration rates during this time period from the remote sensing over here. Okay, so what are the potential hydrologic implications of these differences in subsurface moisture content? Well, one interesting thing that we observe in this landscape is that we have these shallow groundwater wells, which are kind of situated at that interface between the saprolite and fractured bedrock. So this is shallower than that deep groundwater table I was talking about earlier on. And what we see is that on the south-facing slope, we have this shallow groundwater response during these winter precipitation events. On the north-facing slope, especially in the upstream or the kind of the top parts of the hill slope, we actually don't see that response. Instead, we only see this near stream response on the north-facing slope. So this is kind of suggesting that during precipitation events, because of this smaller root zone storage deficit and a wetter subsurface, we might expect more groundwater recharge beneath the south-facing slope. And then in the north-facing slope, during these precipitation events, because the subsurface has this root zone storage deficit, that incoming precipitation is instead going to refill that pore space and is not contributing to groundwater recharge. And this raises the question, does the south-facing slope contribute more to stream flow than the north-facing slope? And that's something that we're still trying to tease apart in this landscape. Okay, the final thing I wanted to leave you with is thinking about how these landscapes are going to respond in the future. So the south-facing slope with more insulation they're not suitable for oak tree regeneration. So what I showed you is that there's actually water in the subsurface, but in that really thin soil layer that matters for tree regeneration, it's dry enough because of the greater insulation that oak trees are not able to survive. And this is what leads to these aspect-related differences in vegetation. But I think it's an open question about whether, with a future warmer climate, how these north-facing slopes will respond and whether they'll be able to regenerate oak vegetation in the future. Okay, so to wrap it up here, a couple take-home points. First, from part one, deep fracturing causes high permeability in a deep water table that controls the onset of chemical weathering and interbasin water flow. For the second part, despite receiving roughly 2 times greater solar insolation, south-facing slopes show greater rock moisture content than north-facing slopes due to water use by woody vegetation. And then finally, big picture, I hope what I showed you today is that really to understand some of these hydrologic processes and landscapes like this, we need to think deeper and think about this deep critical zone structure, which I think is important for thinking about how we manage these systems under a changing climate. And that's all I have, so I'd be happy to take any questions. Yeah, that's a good question. One idea we had was potentially trying to do, some sort of tracer test or something to see if we could, during these these precipitation events, if we could actually observe, differences in contributions from the north versus south facing slope in the stream water. The tricky thing with these systems is that the streams really only flow during these really intense precipitation events. So trying to figure out whether that water that's in the stream channel is sourced directly from that precipitation or something that's stored longer term, I think is a bit of a challenge. Sure, I don't know. Go ahead. So yeah, we just simply did it by taking we had the measure, let's see, to it. Yeah, I mean, we were surprised too, honestly. So this is from the elevation of the water table from the two wells, and then the water table from the in-stream well here. And that's just, drawing a straight line across with nothing. We only have three data points, but no, I mean, these are all, within 2 meters of each other. These three measurements, 2 meters of elevation of each other.
What's this scale?
This is probably like 2 or 300 meters across, 2 or 300 meters from S3 to N4. Yeah, I know.
That's still
Right.
just if there are vertical hydraulic gradients where you have those two wells, the only way you can actually delineate the water table well is finished exactly at the water table. Other
Yeah, I'd be happy to chat with you more about it. I mean, there's a pretty simple, we were just trying to connect across, and these were finished, open throughout. So I don't think, I don't know.
I simply question whether or not
The water table or not. Yeah, that's fair.
minerals.
What mineral was the fractured bedrock? So there's a couple different minerals throughout the rock. This is all, there's like a lot of quartz because it's a sandstone, lots of feldspar, the oxidation we see we think is probably, oxidation of feldspars and stuff.
I noticed that in your pores, it looks curious why you think that is.
Yeah, that's a good question. Yeah, this is like totally it's super fractured over here. I don't know what's driving it. I don't think we have enough, evidence. I mean, like drilling here, it's like you would, you'd be through something that seems competent and then you would just like hit what seemed like a big fracture zone or something like that. But, so that kind of makes me think that, kind of supports this idea of the really high permeability where especially we have these fracture zones that are, seem to be really wide and probably like moving lots of water. As far as for the, permeability, like differences in water table, I'm not super sure across the slopes.
Why is this?
Yeah. So, I mean, originally this was motivated by these slope aspect differences in vegetation. That's what like the grant that funded this was motivated by. And I think another important aspect of that I think is important is this potential like kind of complex geologic history and tectonic environment that makes up a lot of different landscapes. I mean, oftentimes when we want to study something, we go to a simple place, right? Like I did all my PhD work in the Sierra Nevada, which is just it's more complicated than that, but essentially a big block of granite, where things are a little more simple. But when we have these things like melange geology and fault zones and stuff like that, I think that's kind of an understudied portion of critical zone science a bit.
Specific vegetation here.
Yeah. Yeah, that's a good question. I mean, I think, especially in these Mediterranean climates, right, the deep, that's where you have the deep-rooted vegetation and that the reliance on this water stored in the weathered bedrock rather than the soil. I think especially with this second part and the aspect-related difference in vegetation, I think, these findings, I think, are somewhat specific to rain-dominated systems. And once you get into snow-dominated systems, you have, the differential melting on north versus south-facing slopes, which probably changes the moisture dynamics a little bit more. Likewise, where it rains more, these, aspect-related differences might be less pronounced, especially like, I mean, I've done most of my work in the Western U.S. and now I'm like in Connecticut and I'm like, what do I work on? Everything, all the trees only care about like the top 50 centimeters in Connecticut. So, I think that is an important part of this work is that, it really is, some of these findings are really specific to these Mediterranean climates, and where it rains more and the subsurface is replenished more often, these patterns are different. Not, I think we're in these mountain landscapes where, we're not in these like depositional zones where lots of hydrocarbons are important. And when we were drilling, we didn't really see any sorts of evidence of this because it's, kind of this active erosional system where those sorts of things aren't going to be filled up. Yeah. Well, yeah. So that there's been, some folks who have tried to regenerate trees on these south-facing slopes, and I think what's really limiting them is that really shallow moisture, right? Because when you're regenerating, those small trees haven't yet tapped into that deeper moisture yet. So it's really that top 5 to 10 centimeters that I think is limiting them. Another question up here. Yeah.
Oak regeneration.
Mm. Yeah, that's a good question. There's this interesting, I think, kind of feedback too with these, especially with the regeneration, is right. Once you have mature trees, they shade, and it's easier for those, saplings to regenerate underneath the shade. And then, if you have wildfire come through, that could actually, if it's severe enough and you have, mature trees dying, then that could potentially, be a feedback where it's actually harder to regenerate in those areas. I'm less familiar with, the specifics of, why the oaks preferring burned areas? Is that like what's the mechanism for that? Oh, okay, gotcha. Fair enough. Yeah. I'm not familiar with that literature. I trust you on it. I was just curious what the specifics were. This site actually burned, but it was low severity enough that the mature trees didn't die. So.
I'm really struck.
I mean, you could do a back of the envelope and just, using the evapotranspiration, but we haven't tried to quantify it with our groundwater wells or anything. Are you just talking about? Right. I mean, so what are?
Difference between coincidence.
Mm-hmm.
Water and energy.
Right, but I think, especially in this system, I'm not sure that water is staying at the surface long enough for that evaporation to happen. I think it's largely driven by the transpiration of the vegetation, because the permeability is enough in the soil that once it rains, it's recharging and not hanging out at the surface where those differences in insulation and energy are affecting it.